here. Peng has been working on a large variety of different topics, 21 centimeter related, visualization, galaxy clusters he will be talking today. And he has been doing his undergrad in Chicago, then went to Princeton for his PhD with and moved from there to Caltech with Mark Minkowski, and he already said that he took away half of his talk, but I'm sure that he will have a very entertaining and long, interesting talk.
So thanks Jens for the invitation. It's really great to be here. Every time I come to CITA, I eat so well and I drink so much. I really enjoyed my time here. So as Jens said, I had a bit of a de-scope. The cosmic ray part sign of the result oscillates. But I'd be happy to talk to you offline about that. So it's not quite ready for prime time. But first, I'd like to thank my collaborators in these projects. The main bulk of the stuff I'll talk about was done with Matthias Ruskowski in Michigan, and some new stuff on predictions for Astro H with Xian Shang, who's a postdoc at KITP. And I'll mention a bit of work that was done with my former student, if you like, who will accept these. Okay, so in CITA, you know clusters as something you can do precision cosmology with, right? And you can do fundamental physics. When we were organizing a workshop last year, and Dick Baum said, don't have too much weather in it. This kind of stuff is where the action is. But unfortunately, I like weather, and weather turns out to be important. The SZ was really supposed to be a very fundamental measure of cosmology, but you have horrible things like weather, and the SZ is kind of a complicated diagram. But the basic thing is that the SZ amplitude turned out to be lower than what the first predictions thought they should be for a given value of sigma 8. And the thinking now is that there's some form of turbulent pressure support in the outskirts of clusters, which reduces the thermal signal. Right? So it behooves us to try and understand some of this weather. And I came to this from, I started out in IGM because things are nice and simple, and most of the time you don't have to put in some great prescriptions, and it's something that a simple mind like mine, can get around. You try to go to galaxies, it's really hard, right? It's difficult to say something with confidence. And I think the ICM is a nice middle ground. It's more complicated, right? So there are horrible magnetic fields you have to worry about. But it's sort of a test bed for ideas about galaxy formation, right? You can see the effects of AGN feedback. You have this nice, huge thing on the sky, which basically is a closed box. You can see it in a bunch of different wavelengths, like X-ray, SC. You can see optical in galaxies. And the densities are lower, and timescales are longer. So you can have some hope of, things aren't too horribly nonlinear. And you could try and see what's going on. So anyway, that's what I put in proposals. So the first thing I'll talk about is interaction between turbulence and conduction in galaxy clusters. I'm hesitant to talk about turbulence in front of Peter, but we'll go with it. So the motto is that I'll try to leave you with is that these two interact in a very intimate way in the intercluster medium. That conduction enables gas motions to happen more freely, so it reduces the effect of gravitational stratification in a cluster. And in turn, turbulence scrambles the magnetic field lines so that conduction can flow more freely. So why should we care about conduction in clusters? So you've all heard of this cooling flow problem that's really not a problem, right? Because although you see copious X-ray emission, you don't see a huge amount of cool gas in the center of clusters. So you need some kind of heating source, and you actually need a couple. So we see AGN heating, right? We see these X-ray bubbles with Chandra, but they're generally not enough. And energetically, you need something a little more. And conduction is a very attractive candidate, right? You see this temperature gradient, and it's easy for heat to flow down. And if you just do simple estimates, some fraction of Spitzer is good enough to offset cooling. Although these conduction solutions, if you just have conduction, they tend to be unstable. You either become isothermal or you develop a cooling catastrophe. So you have to tune the level of conduction somewhat, and that's not very satisfying. So usually what happens is if you put in an AGN, it's much more stable. And you can kind of see this if you do, say, a global stability analysis, where you have both of these heating mechanisms. And you can see that you can have two forms of solutions. Either a solution which is, has a cool core, which is stabilized by AGN and conduction, so the temperature declines towards the center, or something that's fairly isothermal, where only conduction operates. So if you want conduction as a candidate for offsetting cooling, a lot depends on what your magnetic fields are doing. So if you have radial fields, that's great. If you have tangential fields, that's terrible. And if the fields are scrambled, then as long as the coherence length of the magnetic field is much smaller than the temperature scale height, but it's still larger than the mean free path, then you can treat this sort of as a random variable, and you should get about a third of the Spitzer rate. So which of these is it? The trouble is that you can't choose the magnetic field configuration freely. So there's various buoyancy instabilities which tend to align the magnetic field in different directions. So in the outer parts of the cluster, where the temperature declines with radius, you can show that there will be something called a magnetothermal instability, which will make magnetic fields radial. In the inner parts of the cluster, where temperature declines inwards, you have something called the heat buoyancy instability, which will give rise to tangential magnetic fields. And it's actually interesting that this was discovered so late. So there's still interesting surprises in this field. And how does it work? You can draw a diagram just like you do for, say, Schwarzschild instability, right? Convective instability. So if you have two fluid elements and they're connected by a field line, then as long as the conduction time scale is shorter than other time scales in the system, specifically the dynamical time, then they'll tend to be at the same temperature. And if your temperature increases outwards, that means if you raise a blob, right, it's connected by a field line here, so it will be colder than its surroundings, and in pressure equilibrium will be denser, and so it will sink. And you'll tend to establish tangential field lines. And this was discovered by Elliott in 2008. And if you run simulations of this, then the field lines rapidly become azimuthal, essentially on a few buoyancy timescales, and the heat flux plummets, and you get a cooling catastrophe. So that's not good for those of us who had high hopes for conduction. But in general, what you expect is that it's not sitting around in nice static equilibrium, right? There's stuff moving around the cluster. And you expect, maybe turbulence is too strong a word, you expect at least mild subsonic motions in the intercluster medium. You have galaxies moving around, you have AGN, you have minor mergers. So there's some circumstantial observational evidence for these motions. They're all predicted by simulations from structure formation. I'll talk later about how hopefully Astro H will really provide firm bounds on gas motions. But the idea is, in simulations, what people see is subsonic motions with sort of Mach numbers of, 10%, 20%. Could these things randomize field lines and restore conduction? So the bottom line is yes. Okay, so these are 3D flash simulations where here we do not stir the box. We just initialize it with a temperature profile that you expect from observations. And you can see the tangential field lines arising from the heat buoyancy instability. And this insulates the core, and you get a cooling capacity eventually. Whereas here, we stir the box, right? And you scramble the field lines, and you actually restore conduction. So, great, fine, whatever. It's not. The thing that was interesting was how little stirring you needed to scramble the field lines. You didn't need very much motion at all, which makes it plausible. So the simulations are 3D flash simulations. It's AMR, so you have a pretty high resolution. And we put in turbulent forcing by hand, meaning we just stir the box with some spectral implementation. So later on, we took a step further and we tried to say, what if galaxies can do the stirring by dynamical friction? So that, and then that doesn't, that has a, then you're not sort of putting things by hand. So that had some interesting results. The required amount of turbulence was remarkably small. I think that was the most interesting thing to us. Something like our strong stirring case was 3D velocity dispersion about 150 kilometers a second. Weak stirring 50 kilometers a second. So even this, that's about a 10-15% Mach number. Very highly subsonic, right? But you can see if you look at this isotropy of the magnetic field, defined in the same way as for dynamics, right? So that isotropic is beta of 0, tangentially biased is highly negative, and radially biased should be 1. So you can see that if you didn't stir the box at all, you get these enormously tangentially biased magnetic fields. So you have this is the pure HBI case. But really, with this very weak stirring, that stops that. And with 150 kilometers per second, you basically go to isotropic fields. If you plot the Spitzer fraction, conduction is essentially restored. The world is safe again for these hybrid models of conduction and AGN. So why are such weak motions effective? It's basically because your restoring forces are much weaker in a conducting medium, right? So you all know the standard case state in stars, where you're stratified by entropy. If you displace a fluid element, right, it conserves entropy if you displace it adiabatically. And so you receive a restoring force, which is essentially proportional, the frequency is essentially proportional to your dynamical frequency and the logarithmic derivative of the entropy. But here, because when you displace a fluid element, it's connected by field lines, what you conserve is not temperature, entropy, but you are displaced at constant temperature. So your density contrasts with the surroundings, and so the buoyancy force you feel depends on the temperature gradient. And the temperature gradient is much weaker than the entropy gradient in clusters. Right? It's very strongly stratified by entropy, but clusters can even be close to isothermal, in which case you are in a state of neutral buoyancy. So the buoyancy forces are much weaker, and so it's very easy to mix up the medium, to stir it and sort of randomize the field lines. So you can formalize it in terms of a Richardson number or a Froude number, and if you stir it at very low frequencies, then you can't overwhelm the gravitational stratification. But if you stir it at frequencies higher than this pretty low frequency, then you can achieve sort of, you can isotropize all your motions. And this velocity that you need is extremely small. So
why is the temperature suddenly constant? Is it because of the cooling being very temperature dependent? So that no matter how much you heat it, you always end up at the same temperature? I would have thought the cooling, what is the cooling? Is it Bremsstrahlung?
It's Bremsstrahlung and line cooling. But I don't think it's so.
Cooling can be very temperature dependent.
That's true.
Bremsstrahlung isn't.
I think it's more because the stratification and entropy is easy to understand. And then if you're strongly stratified with entropy, then if you cool a bit, you tend to sink in the medium, and that will heat you adiabatically, right? So you'll reach a higher temperature.
It's not completely. You want more than just a factor of 2 out of this.
No, you actually the difference in the temperature and entropy gradient is not huge. It's like a factor of 2, a factor of 3 in the logarithmic derivative. But that's enough to make a difference from a Mach number of, say, 15%, which is very plausible, to a Mach number of half, which is not plausible at all.
Well, it doesn't have to be stratification. It has to do with whether you're adiabatic or within your parcel. So if you move a parcel and you maintain its heat content,
right?
Then you're going to go back down to your density.
That's right. Then you'll depend on the entropy
You
gradient.
can keep that parcel
Right.
isothermal if you move it around.
Right.
Because of rapid
Right.
conduction.
So the whole point is that this is not an adiabatic process. Right. So the conduction is faster than
It
that.
doesn't matter if it makes a difference what the background.
No, the background matters because that determines your reference density, right? This is buoyancy-driven instability. So it's the density difference that drives how strong your restoring
Right.
forces are. Yeah. So if your background has a very strong temperature gradient, then you'll have mostly tangential motions.
So in the simulation that you showed results from, you were continuously stirring.
Yeah.
You were continuously stirring the long wavelength
That's right.
at low K, and then you were looking at, and you put in some field initially.
Right.
And you were then looking at seeing how the field developed
Yes.
as the stern went on. Was it purely located?
It's driven at a spectrum of so it's not just at low K. It's driven at a bunch of K, but it's sort of it's the standard routine that people in Flash use that gives you the right.
It's like this is my point. So you mentioned you did some other ones where you tried to motivate the stirring.
Right. So I'll come to that.
Okay.
Yeah. So this one is just stirring by hand. So there's no cooling catastrophe, right? You restore conduction. It becomes somewhat less of a cool core. But the interesting thing is that this thing is now stable, and we don't have an AGN in the center. So normally, if you have conduction only, you either become isothermal or you develop a cooling catastrophe. And this doesn't happen here. It's stable without an AGN. So, so that's kind of a curiosity. I'll talk a little bit more about this.
Let me ask one more question so I understand what you did. You have a thermal conduction in your simulation,
Yes.
which is a tensor,
Right.
and it's much higher along the field than across the field. I have appropriate ratio.
Yeah, we completely suppress cross field.
Oh, you just make it zero.
Okay, so so we put in stirring by hand. It works. But most sources of turbulence that you can think of are somewhat intermittent, like mergers or AGN outbursts. So what really could be doing the stirring? One thing that's a very good candidate is galaxy motions. So dynamical friction on galaxies moving through the cluster. So it's not just solid bodies that feel dynamical friction. Gas can feel dynamical friction too, right? And you transfer energy basically from the motion of the galaxy into that of the gas. And this is not a new idea, of course. People have looked into dynamical friction as a way to overcome cooling in the cluster. The trouble is that the amount of energy you transfer is actually small. But we don't need very much motions to randomize our field lines. So we could just use this, tap into this as a way of stirring up the gas.
Well, if you were transferring a lot of energy, all those galaxies would fall to the middle.
Exactly.
Especially since there's much more mass gas.
Exactly. Yeah. Yeah. So, but people wrote long papers about that, but you can immediately argue that. Well, so, but the trouble is that galactic wakes, if you do some estimates, the wakes actually have a fairly small filling factor, right? And if you really want to have conduction throughout the entire ICM, then you want to scramble the field lines in a fairly large volume fraction of the gas. So one way you could make stirring volume filling is if you can excite G modes, right? So if you can stir something at very low frequency, so frequencies lower than the Bragg-Varsaler frequency, then that will excite very long wavelength mode, right? Which allows global motions, and then that will move down to smaller scales. So basically, what you want to do is track some modes. So can you do this, right? What the tracking requires is that you stir the medium at very low frequency, right? But to overcome restoring forces, in order for you to isotropize magnetic fields, you require that motions have high frequencies, right? But you can stir the medium at low frequency on large scales, and as it cascades down to smaller and smaller scales, frequencies become higher and higher. So that's the hope, right? Oh, maybe this will work, but it's hard to tell unless you actually run a simulation. So what we did was, we sort of guesstimated what, you can't sort of do this from, you can try to start doing this from cosmological initial conditions, but it's really hard. So we just built a cluster in the box where we put in galaxies with some profile consistent with lensing observations. And we initialize the gene's initial conditions, so it's consistent with the gene's equations. And we let it run. And it works. Right? So as time goes on, you build up some medium velocity, which is sort of consistent with the estimates that from the stirring box that we made before. And the magnetic field becomes more and more isotropic. It basically approaches isotropy. And there's no cooling catastrophe. So what you have here in the shaded regions are the time to the cooling catastrophe in gigayears. And basically, if the mass and substructure is sort of like what the simulations tell you, the lensing observations tell you about, 15%, something like that, then the time to cooling catastrophe is longer than the time between mergers. So, so we were very happy with this. I mean, it's still somewhat idealized because it's not from cosmological initial conditions, but it's consistent with observations. And the thing we were really happy about is that this doesn't have subgrid physics. The thing with a lot of this kind of game is that, for instance, if you put in an AGN, right, you always need some way of transferring energy from the AGN to the surrounding intracluster medium, and making sure that even though it's injected this way, it's isotropized. And that's kind of a hard game. So people essentially have to put in some kind of subgrid viscosity, or played around with the subgrid prescription for cosmic ray heating, something like that. But there's no subgrid, so conduction is resolved, right, because you have fuel resolved conduction. But why isn't the cluster becoming isothermal or encountering a cooling catastrophe as you have for conduction-only solutions?
Maybe I should. You do have subgrid non-physics because you're not resolving all the turbulence.
No, that's true.
So,
but the idea is that
you have a grid scale in which energy disappears.
Right. So there's an effective viscosity in the simulations. But you can show that the dissipation of that turbulence is extremely small. Basically because the energy density in turbulence is so much lower than the thermal energy density that it can't be providing significant heating.
So let me understand, when you put this energy in by either galaxies or stirring or whatever it comes in with, is most of that energy lost to radiation or?
No, it eventually dissipates by numerical viscosity.
So it all gets dissipated by numerical viscosity.
But the amount of energy that you're putting in is much less than the amount of energy that's being lost by radiative cooling. So yeah.
Okay, that's fine.
But you'll have numerical heat conduction as well across the directions. You have one of them, but you have cross field conduction numerically.
Yeah, but in the case where we don't stir, basically you always have a cooling catastrophe. So that's just another way of tapping into the stirring motions, right, to dissipate energy. Because your ultimate heat source for that is the motion, right? And the amount of energy in that is very small. So, I mean, you're basically talking about numerical resistivity, I guess.
It's not clear to me when it means external stirring situation. It seems perhaps there's a loophole or having choice for if I have an inhomogeneous magnetic field and the fluid comes into some local buoyancy equilibrium, the density is more uniform than the temperature across it. And that means that even the stronger field will have lower temperature. So there's a feedback between the magnetic field and the cooling process.
The field strength basically doesn't really matter because
what I'm getting at is not the effect the magnetic field has on the anisotropy of the conduction, but on the rate at which entropy is removed from the flow locally by radiative cooling.
There's an inverse correlation between the strength of the field and the density of the medium.
But it's the pressure due to the field is much lower than the thermal pressure. So the field is like
But
microgauss.
this is, I can go over the maybe interesting feedback here, so
Okay, all right,
not now.
all right, okay.
As part of the most so the side is very, very big weights using dynamic, using the stirring of the gas to classify certain weights, which you want to decide gravity waves in the cavity, and then you want them to break down to turn over to generate turbulence.
That's right.
These are really weak gravity waves, right? I mean, are they really going to be strong enough here, and therefore,
I mean, what I can tell you is that we have galaxies in a box, and if we change the gravitational potential, so if we took away the CD galaxy, and we change this the shape of this curve, then it was much harder to get the required stirring for the same galaxy population. So I don't.
city gas is sitting in the middle, right?
Yeah, but the CD galaxy, changes the Brown by-Sala frequency in the middle, basically. So somehow, if you don't have some trapped G mode or something, that region didn't have volume filling turbulence.
But here it is trapped, so it is not in it, isn't it?
But what you need is just very weak. You just need very weak motions. You just need them to be volume filling, basically.
Is there some mechanism for the gravity waves to grow in amplitude when you don't have any volume, or like density?
Well, I mean, basically they sort of get trapped, get amplified.
But that's why you want the frequency. You're getting a slide earlier where you want excitement low frequency, but then using a high frequency. So
Right, but it's at different scales.
exactly. So
Yeah.
you need some kind of breaking of the low frequency.
Yeah, so you need them to cascade to small scales.
Right.
Yeah.
Right. You need a cascade.
Right.
But like the cascade will happen. That's my question.
Well, that's the way we explained, being, the change of the CD galaxy changing the Brown by-Sala frequency, being able to affect whether you get volume filling turbulence or not. So, actually, that's a good point. Look at this. Good thing about that.
Well, the gravity waves are going to have a local interest in it, right? Which is the ratio of the potential shear flow return time scale to the buoyancy return time scale. And that needs to be sufficiently small for the yield to return the shear time.
Yeah, I mean the gravity waves themselves, will have they'll have a Richardson number that's not sufficient to overcome the restoring forces.
Just how do they break? Right, so that's
Yeah, I know. So you have to sort of amplify them instead.
Well, you actually see this in the simulation.
Yeah. So we're just trying to extrapolate from what we saw.
Explain what you see.
Yeah, exactly.
Okay. Well, when you have a magnetized medium, you have a weak turbulence.
Right.
It doesn't behave like hydroturbulence. It gets stronger because the cascade is anisotropic. It gets stronger and stronger because the cascade only occurs in two dimensions. And ultimately, it becomes strongly nonlinear, and then it does give, or will give a Kolmogorov type cascade.
Right.
Well, the question is, in the simulation, there's no actually physics.
No, there is, I don't know.
There's no.
Is the MHD in the dynamics or only in the conduction? And is the magnetic field treated kinematically or is it dynamic?
Well, magnetic tension is not important. That's what I mean.
Oh, okay, well then you have a problem. It's hydro with anisotropic conduction.
Yes. Okay, so that's a good point. So maybe the explanation for this we have to work on it, but definitely we see it in the simulations. Okay, so the fields are amplified. Not too surprising. Sort of mirrors vorticity as you might expect. The thing that was kind of interesting was that conduction was important in the outskirts, but really what was important in the inner regions was turbulent convection. Okay, so you can find the ratio of heating to cooling, and in the outer parts, it's mainly conduction that's doing the job. But in the inner parts, at late times, so the blue curves are late times, turbulent heat flux is actually more important. And so that turbulent heat flux basically plays the role of your AGN, the volume that we had before. So, another interesting thing is that, well, we were always worried about how AGN, transfer heat to the surroundings. Well, maybe if they just stir things up enough, they just tap on the outer heat reservoir and use turbulent diffusion of heat to offset cooling in the center. So, here you have stable solutions which are not necessarily isothermal. Right? At this part, cooling is offset by turbulent heat diffusion. And you can have these sort of temperature fluctuations sometimes if you bring in a high entropy material inwards, and you can see little upward temperature fluctuations. So, that's sort of a signature of these kind of things. So we see something like this in observations that would be very interesting. Another thing is that this sort of sudden injection, if you allow conduction to operate, right, it can modulate a transition between a cool core and a non-cool core. So here's a simple, very 1D simulation where we suddenly allow conduction to operate more efficiently, and it transitioned very quickly to a non-cool core cluster. And so there's sort of two stable states, right, which is consistent with what you see in observations, right? If you plot the central entropy of clusters, it tends to be bimodal. So if you really want to tell if conduction is an important part of the story, it would be very nice to be able to look at groups, right? Because Conduction is very temperature dependent, right? It goes as T to the 5 halves. And group temperature is too small for conduction really to be important. So you can see that, here, all the lines thicken only for a sort of cool core type profile. If you kick up the conduction or you try to keep the medium somehow, it will always relax back and that will never settle to these kind of solutions. And this is consistent with central entropies you see in groups, but I wouldn't take this too seriously because a high entropy group has a low density core, and so it's harder to pick up in X-ray surveys. But it would be very nice if we had deeper surveys to sort of look for these kind of things. So that's sort of I think maybe a signature of which would be able to tell us if conduction really is such an important part of the story. So just for this part of the talk, the basic idea is that this yin-yang thing, that conduction can enable turbulence because it weakens restoring forces, and turbulence can enable conduction because it scrambles field lines. And this statement is for global stability. So it'll also be very interesting to look at how turbulence affects local thermal instability. A lot of people think that maybe filaments in clusters form due to local thermal instability. So we're currently looking into that. Okay. And then the last 10 minutes, I'll just sort of tell you a bit about this little tool that Xiansheng and I built to try and see, well, what can you do with asteroid H, right? So this whole story about turbulence, there's a lot of circumstantial evidence that there's turbulence, but really what you want to see is our turbulent broadening of spectral lines. And there's been a bunch of attempts to see it. This will be the third one to launch this satellite. Hopefully it will not run out of coolant or explode this time. Well, if we can see the actual broadening of the lines, then that will really be a smoking gun signal of these gas motions. So it's sort of engineered for this task. It's got the spectral resolution. The full width half max corresponds to a 3D velocity dispersion, just like the velocities I was talking about. So we'll be able to see this, and it will be great. The main thing is that asteroid H has horrible angular resolution. So the angular resolution basically corresponds to about 100 kiloparsecs for most nearby clusters. But the great thing is that it'll have a lot of photons. You can probably collect about 10 to the 4 photons in sort of the iron K alpha line, like 6.7 keV line. So well, hopefully we'll be able to see this turbulence. And all the sort of broadening are roughly comparable, right? The contribution from turbulence, contribution from the instrument, and thermal broadening, all roughly the same. So most of the current thinking is now, well, we'll measure the line width, and that will tell us the turbulent energy density.
Wait a second, you're going to measure the line width of the light and the heavy together, and then you're going to separate the thermal and the turbulent? So you're going to just do
yeah, you could try some other lines, but the main bright one is this iron line. So you're going to assume that you know the temperature exactly from other X-ray measurements. So you can assume all other broadening is due to motions.
Okay, so the iron is an advantage because it has very little thermal.
Exactly.
But
Yeah,
isn't
it's
it true
nice
that,
and heavy.
isn't it true that depending on the eddy size, along the line of sight, you anyway don't get just one line with the broad, but there might be like.
Exactly.
So I mean that's
exactly. So we just tried to do this, right? So it's not really going to be Gaussian, right? So the eddy size is large compared to the scale of the system.
Yeah, but you're interested in typical turbulence. The biggest velocity differences are across the biggest eddies, which are the ones that contain all the energy. And so if you just go through some system, the turbulent velocity you get is that of the biggest eddies, which contain all the energy to do most of the mixing. So,
Okay, anyway, I'll do a cartoon to show this.
I actually heard the talk on something like this from Rashid Sinai.
Yeah, so we're trying to, so what he looked at was basically the shift in the line and the spectral width of the line. But, okay, anyway, I have the story. So the story is that you have a bunch of things going on. You actually have Hall motions, right? Fairly laminar motions, which will introduce additional structure. And this is something that we actually see. So for instance, we see cold fronts in clusters, right? So these are very sharp contact discontinuities where temperature and density change suddenly. And there's this whole picture sort of spearheaded by Maxim Markovich, where you're supposed to think of it as sloshing, gentle sloshing within the gravitational potential well of the cluster. So here's an ENSO simulation that CM ran, and it has all the classic signs of the cold front, this sharp change in density and temperature, but pressure is continuous, so it's not a shock. This gives you a line which is pretty different from just trying to measure a line width. Okay, so here, if you look along this line of sight, if you happen to look at the cluster along this line of sight, you would get something which looks like this. So two separate peaks. So the idea is that, well, we can try to use this to separate out bulk motions in the cluster from these much smaller scale turbulent motions. Okay, and you can see there's a clear bimodality here. If you look, it depends on your viewing angle. If you're very unlucky and you look along this line of sight, then you would get something which looks sort of much less clearly bimodal, but there's a long tail. And so our claim is that there's actually information in all this structure. And what I wanted to do is that since a lot of broadening comes from thermal and instrumental broadening, which is Gaussian anyway, let's just represent it as the Gaussian mixture model. So this is a regime, when you have a cold front, when the difference between the mixture of Gaussians is set by the separation in the means. You can also have another toy case where say, whatever G-mode story I tried to sell you didn't work, right? The motions in the gas are streaky. So there's some parts that got stirred up and some parts didn't. Then you would have a component that just had thermal and instrumental broadening, and an additional component, right, which is emission weighted, which has in addition turbulent broadening. You add these two up, you get something which looks just like a regular Gaussian. Right? But if you apply a Gaussian mixture model, you can actually uncover these underlying components. So we call this, the width-driven regime. So there's a sum of components with different widths. So, all right, so let's try. This mixture modeling has a huge history, so I tried to learn some of it. It was actually first used by Carl Pearson, who's like very famous Pearson correlation, blah blah. And he used it on a population of crabs to try to separate. There seemed to be this like weird skew in the distribution of their, I can't remember now. It's like torso to claw length. Okay, something about the crabs, okay, was different. And people are trying to fit all these skewness, just like cosmologists love to expand things in bispectrum and all of that. But Pearson said, hey, I can fit it really well if I fit it as a sum of Gaussians, right? And this apparently was the first sort of quantitative evidence for evolutionary divergence. So it's kind of cool. So these mixture models suffer from a missing data problem, right? If you know you have a sum of two Gaussians, then you just have to collect data points for this one, collect data points for this one, and then estimate the mean and the variance for each. The problem is that you don't know which distribution the data point belongs to.
So are you summing the PDFs, or are you summing the random variables?
we end up just looking at what the simulations tell us, right? And then we try to decompose it into gaussians.
You stick the PDFs and try to work on the superposition.
Yeah, that's right. Yeah. Okay, so the big literature on this, I tried to read some of it. I implemented a Bayesian version. I felt very proud of myself. I wrote out this MCMC code, whatever. And then it works. Okay, you have a test case which has roughly, this one is just thermal. This one is thermal instrumental. This one is thermal instrumental and turbulent bonding. And here's the here's the histograms, the recovered parameters. This is the input. All works well. Blah blah. And then I was talking about this with Xian. And he said, well, why don't you just do chi-squared? And I was like, nah, chi-squared's stupid, it won't work for all these reasons, blah, blah. Look, I read all these fancy books, I know what I'm talking about. So he said, well, let me try. so okay, fine. And then, you can't do chi-squared because the residuals are not Gaussian. But, because, when you look at the tails of the distribution, there are not many data points. But the residuals are more or less Poisson distributed. So if you just do a cache C statistics and try to minimize this, so this is the number of data points that are observed, and the number of data points that are expected. This is basically a Poisson likelihood. Okay, he did this, and then he got the same results as me, 100 times faster. I was so depressed, but then I said, okay, fine, you do it. So he confiscated my elephant gun, and then he pulled it through for a whole bunch of different cases. So so first we tried to play with some toy problems just to understand how this thing works. We set up just a 2 Gaussian case, and then you have 5 parameters, right? 2 means, 2 variances, and then the relative component in 1, and the other one is 1 minus that. And basically, the parameter which controls your errors is something fairly intuitive. The separation between the means divided by the sum of the standard deviations. Right? Maybe we should have taken squares and taken square root, but something like this. And you can understand the error scalings quite easily. So so in this regime, they're very clearly separated. And you just have shock noise, right? So the errors are about 1%, which is reasonable if you have 10 to the 4 data points. And then when you bring the 2 Gaussians closer together, right, there'll be confusion noise, right? But then at some points, your errors are set by the ratio of the variances, and you are in a different regime, a width-driven regime. I talked about. You can compare MCMC error bars with these particular data points are not right for some technical reason, but the rest are the MCMC and Fisher matrix calculations pretty well. So the bottom line is, we did this for all the parameters. You can get remarkably good accuracy for something you would never expect to be able to separate that well. You just stare at it and be like, well, it'd be really hard to separate. So, the physical interpretation, which is the more interesting thing, we want to attach to the parameters is that the separation is really due to bulk motions or coherent flows, right? Separation between the means of the Gaussians, whereas the variances are due to the small-scale turbulent broadening. And the mixture weight is the emission-weighted fraction of volume participating in each set of motions. So the nice thing about something like this would be, okay, you see your cold front in the sky, right? You have information in the plane of the sky about what's generating these temperature and density discontinuities. But what you like to see is actual line of sight information too about whether there's something like this going on. Okay, so we did a whole bunch of studies in loving detail, which maybe I should just skip. Continuum noise reduces accuracy slightly because some of the information is in the wings of the distribution, and continuum increases shock noise. But if you take the whole ion line complex into account, there's some confusion because lines overlap, but it's overcome by the greater number of photons. So maybe this is too much information. You can have a criteria to determine whether multiple component mixture is favored or not. And basically, velocities, either turbulent velocities or velocity offsets of ordered 200 kilometers a second, and you have at least 10% in one component, then you can state with some confidence that a multiple component fit is preferred. So in the cold front simulation, you actually recover what you get very nicely. So here is the raw data. Here is a fit, due to when you, actually I didn't overplot that. Well, if you look at this table, unfortunately you have to look at the table. Basically, the true values are what you get if you try to fit the data without thermal broadening or instrumental broadening. And once you put those sorts of noise in, you try to recover the mixtures, you still do very well. Even in this case where it looks like it may not do so well. And you can also look at this in the AGN case where you have partial volume splitting turbulence, and you have one narrow Doppler core, and then you have another region which is much broader due to turbulent motions. And you still can get nice parameter recovery. So yeah, so basically, if you fit things with the sum of Gaussians, or at least try to look beyond a single Gaussian and think about the multiple components of the velocity field, then maybe we could learn something interesting, especially in clusters where you see cold fronts. And you see cold fronts in about half of all clusters. And given projection effects, that means that these kind of sloshing motions are probably prevalent in almost all clusters. So it would be cool to see this. Anyway, so that's the two stories. Yes.
So for the so you really only do this with iron gel.
Yeah, there's some other lines. There's a list somewhere. It would be really nice if you could look at some low temperature lines. There's an oxygen line at I think it's like a KE or something.
Can I go down?
It's marginal. It might be possible for Perseus. Yeah.
Follow up to that. So for iron K alpha, that must mean you must have some weight of the cluster towards the center, because for most of the emissions.
That's right.
And is that consistent with where you see these cold fronts? I mean, you actually expect that, I guess, the cold fronts will be more exposed by iron K alpha?
Yeah, I mean these were done for temperature. You convolve the temperature profile.
Let me see if I can summarize what I think I understand.
Okay.
You're saying that in order to get the conduction to be close to Spitzman, 1/3 Spitzman,
Right.
you only need rather weak turbulence mixing.
Right.
And that seems to be a pretty good fit for observation.
Well, at least you don't have a cooling catastrophe.
Yeah.
Yeah. There's no smoking gun that tells you this is really the answer, but
Yeah.
at least you don't have a horrible disaster.
Okay, then also it appears that even in what you might call a mature cluster, a realized cluster, you're concerned about sloshing motions and large scale motions. Now, isn't it then sort of plausible that since almost all of the energy you have to work with is in the binding energy of the cluster, the turbulence is just drawing off the initial energy that is released when the cluster forms at some very modest level, even many dynamical times.
No, it could well because the turbulence is so small that it doesn't have to. And you have minor mergers.
Yeah, you don't have to worry about galaxies. Why do you need to worry about minor mergers? You have this tremendous amount of energy And once the motions are once you have large scale sloshing
Right.
motions, the K in their low Mach number, or modest Mach number, and the K might be fairly low. And so you're just tapping that, and that's enough. You
No,
don't worry about
that's
galaxies
completely
or
plausible.
G-mode.
Right, right. That's completely plausible. But you know, we wanted to say, well, what's the minimal place? You know, we see galaxies moving around. Because if you say, well, you're tapping on the, you know, it's.
But these things aren't that old in some sense.
Right.
That's why you're working on.
Right. No, I think the amount of turbulence we need is very minimal.
Galaxies.
So.
Galaxies are very old. Well, they have many more diameter modes in the disk at least. Worry about, see, you don't think star formation has anything to do with the,
Well, maybe galaxies not. It's orbiting subhalos. In the you know, that could be your spoons. But you're completely right. It could just be residual motions that, you know, live a long time because crossing times are very long.
Well, the wood of that though is that in inner parts it's stable stratified, so you might have residual non-radial motions, but it's not clear that's enough.
So, well, then you maybe you like the galaxies.
I mean, you mentioned this thing about this cultron.
Yes.
That means the activity is small.
Yes. So that people think that's magnetic draping. So you know, when you have the sloshing motion, it tends to drape magnetic fields, you know, across the direction of the discontinuity. So that conduction is very strongly suppressed. You know, it has to be suppressed by at least a factor of 100 or something. But it's, you know, it's the same sort of thing, you know, where you know, you see these bubbles, right? And also there's a very sharp temperature gradient, and people think that the rising bubbles drape magnetic across. I mean, Jonathan Dursey and Christoph Palmer here. I think that's well understood.
So you don't think there's any kind of turbulence that is possible? I mean, intrinsic turbulence that can remove this gradient. I mean, you're increasing the mobility of turbulence. What kind of distance?
Well, I mean, you know, this is a fairly strong bulk motion, right? So these motions are actually transonic, and you know, you just drape field lines across the region of the discontinuity. So I think that's well understood. So people have been looking at these coefficients for a long time. I think it's magnetic draping.
Okay, so Peng is here only today. If you didn't have a chance to talk to him and catch him today. We will also take him out for dinner and let you know if you want to join. And before we go upstairs for coffee and cookies, let's thank Peng again.